All right, so good evening, everybody. I'm Paula King, and Seattle Friends of Fission welcomes you to our Nuclear 101 tonight in 2021. And our speaker is Dr. Nick Touran, a nuclear engineer in Seattle, developing technical solutions to world energy challenges. He's working on the design of an advanced nuclear reactor for nuclear innovation company TerraPower. And he's a clean energy activist, environmentalist, fascinated with all electronics, actually much more. He developed and maintains his website, whatisnuclear.com, which is a great website. And it's to educate folks and answer questions, and he'll always answer questions that people send him. So Nick, it's all yours.
Okay, thanks a lot. Hi, everyone. Excited to be here. Yeah, so this is just this will just be sort of a fun I'm going to go through kind of the basics of nuclear power in general. It's kind of briefly. Well, I don't know. We'll see. I'm aiming for like 20 minutes or so, and we'll see where that ends up. And then, I'm hoping to sort of have a discussion and just sort of hear what you folks would like to hear about, or what what you want to hear more about, or if you have questions that you've been wondering for a long time, just give you sort of a chance to ask those kind of things. So without further ado, I'll just jump into this presentation. So hopefully you can see this okay. And if it's too blurry or whatever, just let me know, and I'll switch to sharing over Zoom the normal way. Yikes. It's not backwards, is it?
Looks fun.
Okay, sorry. All right, okay, cool. It's mostly pictures anyway in here. So nuclear 101. So where do we get our energy? Energy is a replacement for the labor of humans, as you know. We currently, this is 2019, but it's still very similar to this. We currently get almost all of our energy from fossil fuel. You may have thought it was more or less fossil fuel than this, but that's because this is including not just electricity, but all total energy. And so there's this huge chunk, which is transportation, and there's massive chunks over here, which have to do with industrial heat and other things that are not electric. Electricity is only 40% of our total energy, and that's sort of in this mix. So anyway, we have some wind and solar, we have some hydro, and we have some nuclear. Those are all basically non-carbon sources. And then we have all these combustion sources, which are fossil fuels. I should mention that there are biofuels in here as well, and biofuels are combustion, and they're high carbon, and they cause air pollution. So sort of biofuel and fossil fuel are bad, and everything else is good from a carbon and air pollution perspective. And just to sort of reiterate that air pollution is really like the current public health emergency related to energy. About 4 million people die from biofuel combustion when they are burning fuel inside because they don't have access to clean electricity or clean burning fuels. And then another 4 million-ish die every year just from breathing in the particulate emissions from other combustion sources. So this is kind of power plants, and this is biofuel. So we have to get off of combustion sources for this reason alone. But also, of course, there's climate change. And I think everyone here knows that climate change is caused by the emission of greenhouse gas. And if you look at how much greenhouse gas is produced for each kilowatt hour from different types of energy sources, you'll see sure enough that, fossil fuel, biofuel, gas as a fossil fuel, these are very high carbon. And then you have your solar, your geothermal. These are your normal traditional renewables, tidal. And here's nuclear down here at, among the lowest carbon forms of energy we know. So, and this is an IPCC source. So this considers full life cycle from, it's cradle to grave. So it includes the mining for the equipment and the fuel all the way out to decommissioning and waste disposal. So anyway, we need to switch over to these low carbon things for climate change reasons. That I think is pretty mainstream at this point. One interesting and sort of unique thing about nuclear power is that there's just this incredible amount of energy packed into a very small amount of fuel. So, and this is the concept of energy density. It just means how many joules of energy are in a kilogram of fuel. And there's this great XKCD plot where they say sugar, coal, these are your chemical energies. Batteries would be along here. And then uranium, you have to print out. I mean, it's because it's a nuclear reaction instead of a chemical reaction. There are literally 2 million times, there's 2 million times more energy in a nuclear reaction than a chemical reaction. So that's associated with a very small footprint. You don't have to mine a lot of material. You don't have to use a lot of land. You don't make a lot of waste because there's just so much energy in such a small thing. And that's kind of that's the primary reason that nuclear power is interesting at all. So,
Nick,
anyway.
I want to interrupt you so that we can switch to normal desktop sharing. I think
Okay,
it'll look
yeah,
much
thanks.
better.
Alrighty, 1 second. Share. Thanks for interrupting. I appreciate that. Alrighty, how about that?
Much better. And
Okay,
now
cool.
I'm going to put up. Can you change your camera back to your face as well?
Yep.
There we go. That's
something like that. You want me to get rid of the background?
no, background's amazing.
All right, cool. All right, we good?
Yes.
Okay, cool. Thanks for upgrading that. All right, so let's see, and I'll just be kind of looking at the wrong screen, but that's okay. Let me see if I can. Sorry about the technical difficulty. Well, anyway, don't look at me. So anyway, so that's the exciting thing about nuclear. The early applications of nuclear reactors were basically all military. Obviously, there were nuclear weapons, which was one application of nuclear physics. And then another early application of nuclear physics was specialized military reactors. For instance, for submarines, because there's so much fuel in a very small thing, because there's so much energy in a very small amount of fuel, you can load up a submarine with just a tiny bit of stuff and that'll power you for decades. And so all of a sudden you could go underwater. You didn't need to be burning diesel, which needed a snorkel to pull oxygen in. And they went on all these grand adventures. They circumnavigated the world underwater for the first time. They went under the North Pole, under the ice for the first time. And all these sort of incredible capabilities because of that nuclear power source were enabled in submarines. And of course, the Air Force wanted reactors, so we tried building nuclear-powered long-range bombers. And this is actually a picture of a nuclear-heated rocket engine, which is sitting in Idaho. That didn't actually pan out, so we never actually went there, and instead we made ICBMs. That's another story. And then the Army tried making a bunch of little microreactors, truck-mounted reactors that you could deploy to a forward base. They powered a base in Antarctica for a while, a base in Greenland with these small sort of portable reactors you could just truck in, drop in, and run a base. And there was even one on a ship sitting here running the part of the Panama Canal for a while. So these are all the military reactors in the early days. And then, of course, this in 1954, Atoms for Peace became a thing. We tried to get non-military applications of nuclear power. And so we built a nuclear-powered merchant ship called the Savannah, and it drove all over the place. We put a couple nuclear reactors in space, like the Snap 10A. The Soviets put dozens of nuclear reactors in space. We only put this one. And then, of course, there's all these nuclear heated, which isn't a reactor, but the space probes are also powered with a nuclear physics reaction. And eventually we made power reactors to make electricity for the world. And this wasn't until like the mid 60s that this really took off, because it took that long to kind of make commercial scale power plants economical. And so nowadays there's about this many reactors. It's over 400 power reactors around the world, making, as you saw, 4% of the world's total energy. And okay, so you can take a look at electricitymap.org is a great site you can go to and see sort of what the carbon emissions are from each country or region, like live. They're tapped into all the different energy information systems. Anyway, and you can see that like France, which built 50 nuclear reactors in 15 years after the oil shocks in the 1970s, they're very nuclear powered for their electricity. And so they have very low carbon electricity all day, every day. And then you can look at places like Germany, which when, they chose to phase out their nuclear plants before their fossil plants, but they build a huge amount of wind and solar. And so they have very low carbon emissions sometimes, and then very high emissions at other times, depending on how the wind and sun are doing. So you can kind of see different results of different energy mixes just based on what's been done already. So that's kind of exciting. And so we know that like nuclear is a great way to make huge amounts of low carbon energy for, country scale type things. So we have sort of this existence proof that this really works. Okay, I want to talk briefly about, I'm just going to go through like some pictures about what a nuclear reactor is and how it works. So you start with uranium or thorium, nuclear fuel. This was created in supernovas and neutron star mergers billions of years ago. So basically, the Big Bang made hydrogen fused, and that fused to heavier and heavier and heavier things and made stars. And pretty soon stars started blowing up. And when stars are exploding and combining, you can start building really heavy elements well beyond iron and up into the sort of uranium, which are like the heaviest things on the periodic table. And so when that happened, a bunch of energy was like packed into these heavy elements. And so it's sitting on rocks that cooled, and you can go around the universe, including on Earth, and you'll find rocks that have those same atoms that were created in the supernovas and neutron star mergers. So you can go out with a Geiger counter or whatever and find them and pick them up. And then you can grind them up and do some chemistry on them to extract just the uranium out of the rock or the thorium, and take away the rest of the non-nuclear fuel stuff. So this is U3O8, sometimes called yellow cake. So this is sort of a refined natural uranium. Then in today's most common reactors, we have to sort of enrich the uranium. There's two types of uranium, a light one and a heavy one. And we want more of the light one in our nuclear reactors because it's a better nuclear fuel. So we turn that yellow cake into a gas, and then we spin it really fast in these centrifuges. And because they have different weights, they separate a little bit, and you can grab the one that's lighter and make fuel out of that. So once you have enriched uranium, you fabricate it into some fuel form. Typically it's a ceramic solid pellet that looks like this. Is about the size of a gummy bear. And that's it's a ceramic. It's like a teacup type consistency. And so you make a bunch of these little pellets and you stack them together in these tubes. These are just they're like stainless steel tubes, usually zirconium actually, but anyway, they're just like little metal tubes, and they're full of those little pellets. So you stack them up into these fuel assemblies, and those are designed so that to have them in a stack like that allows you to push a coolant through, as you'll see we need in a second, because we're going to make a bunch of heat in here. So then you take these assemblies and you load them up into a giant tank called the reactor vessel. And when they get close together, you can start kicking off this nuclear chain reaction that you've probably heard of, where a neutron splits a uranium atom, a couple extra neutrons come out, that splits the nearby atoms, and so on and so on. And pretty soon you're splitting atoms all over the place, and it's making tons of heat. And so all this stuff these assemblies are starting to get really hot because all those atoms are splitting in there. Okay, so now you have, sorry, I'm jumping around. So you have these rods are getting like super hot, and you're extracting that supernova heat out of these rods. It's real exciting. But so now you have to turn it into something useful. In a submarine, they just boil water and have it spin a turbine that's hooked up to the shaft, and that spins a propeller. But if you want to make electricity, you can do something similar, but you have to convert that heat into electricity. And that is the job of a nuclear power plant. So the core, which is where all that nuclear stuff is happening, is just a little thing that would be down here in the reactor vessel. And all this other equipment is designed to take that heat and turn it into electricity. So you just have some coolant pumps, and you pump a coolant like water past those. It picks up the heat. You boil water at some point. The steam then blows over this pinwheel device, which is called a turbine. The turbine spins, hooked to a shaft inside and then the shaft has a magnet on it. And when you spin a magnet around some coils of wires, you start pushing electrons around, and then you send them out on the transmission lines. And now you can charge your phone and do whatever else, heat your house, and do all wonderful things with electricity. And there is a loop here. So now that you've got the steam, you have to cool it back down to liquid water so you can have it go in a closed cycle. And that's what this big cooling tower is for. So this just brings in water from like a river or lake, cools this steam down into water and then goes out here. So this is always just water vapor, which I think you probably know. A lot of people, it looks like you sometimes see it's like smoke, but it's actually water vapor. And also it's very far away from the radioactive stuff, which is in here. So it's like it never came close to the radioactive stuff. All right. And I'm probably going too slow, but anyway. So then once those atoms split, uranium becomes two little smaller elements that add up to uranium. And those are nuclear waste. They've given up most of their energy, but they have a little bit of energy left, some afterglow heat. And that energy is nuclear waste, is the hazard of nuclear waste. And so we have to put it in big canisters, protect it and keep it contained, because it's going to give out its extra energy, which can be a hazard. So as I mentioned, a huge amount of energy in a very small space. And so if you look at outside these nuclear plants, you'll see like this is half the nuclear waste from 33 years of making 1 billion watts, for all these decades. So it's like, yeah, it makes waste, but it's a very small and very manageable and very well contained type of waste. I recently made this meme. Every spent nuclear fuel cask is 2 million tons of CO2 that never needed to be emitted. So you can look at one of those casks and be like, wow, that's 2 million tons of CO2 if it were a natural gas plant. So that's just sort of a fun perspective on that. So then, of course, they sit in the parking lot until they cool down sufficiently to get loaded up into these more long-term storage casks. And then these are intended to go into deep geologic repositories, like what the Finns are building in Onkalo. So we had a thing in the United States called Yucca Mountain, and that was still is where waste is supposed to go for the long term. And these sort of geologically stable places that you put it in and you don't have to worry about it getting out. We sort of ran into political troubles with that, and so it's basically on indefinite hold. Whereas in Finland, they were like, well, we have nuclear waste, let's solve it. And so they went and they built something at this site called Onkalo. And it's not commercially operational yet, but it's very far along and they've done all sorts of testing. It's pretty much totally built and it should be the first commercial long-term nuclear waste storage facility on Earth. And so that's it. That's people say, what do you do with the waste? And like, here, this is what you do with it, Onkalo. All right. I already mentioned, we already know that the greenhouse gas emissions from nuclear are very low, but what about safety concerns? Obviously, I think when most people think of nuclear, they think of Chernobyl and Fukushima and 3 Mile Island. And so we've taken, or people have gone out and studied what the risk of each energy source is to human life as measured by deaths per terawatt hour of energy production. And as you can see, the combustion sources, because of air pollution, these cause respiratory diseases and all these other complications that come along with that. And it's just orders of magnitude more than the non-combustion sources, including nuclear. And this little asterisk here says, yes, this includes from Chernobyl and the other nuclear accidents. So when you actually, we kind of talk about it like airplane crashes. Like airplane crashes are, everyone can think of an airplane crash, and so we think maybe flying is dangerous. But when you look at the stats, of course, we know airplanes are actually one of the safest ways to travel. And it's the same thing with nuclear. Nuclear is basically undisputedly one of the safest ways to make energy that we know of. And it's just convincing people of that, getting them to go look at the literature themselves is it's just hard, and people don't believe it at first. And so it's like, please go look it up, go to the World Health Organization or whatever. So anyway, it's very safe. All right. And then, okay, but who cares? So obviously wind, solar, and hydro are also pretty awesome on both safety and greenhouse gas, right? So why bother with nuclear? And I mean, I'm not going to say the words that are always said, but like, there's just challenges. This graph shows for a day, this is real data. The solid green is the solar supply, from 6 to the sunrise it rose at 6 and set at whatever 6:30. The demand is this brown curve, and so currently, or this was in 2019, on a nice sunny day in California in the summer, this green is like a pretty notable fraction of the total electricity demand, but of course it has to be, the areas have to equal. So this kind of dotted line is like how much more solar generation you would need to actually meet that whole demand for the day. And then of course, everything that's above the line here, but not over here, has to be shifted with various energy storage technologies or load balancing, shifting, and things like that. So anyway, it's a challenge. It's not impossible. It takes a lot. And then of course you go to winter, and now all of a sudden, the sun's setting way later. There's and rising later, setting earlier, rising later. And there's just this little tiny fraction, but the demand is the same. And so now you have to scale your capacity all the way up to, to this number too. And so anyway, the point is just that every energy source has pros and cons. One of the major cons of wind and solar is just intermittency and dependence on large storage systems. And so there's lots of reason to believe that a combination working together with like the firm low carbon sources like nuclear with the intermittent low carbon sources like wind and solar is probably the ideal scenario. And there's some studies I'll show in a second that suggest that. And, and like it's like, well, if we all know wind and solar are very cheap, they did fall in price dramatically over the last 10 years. But here we have Japan building 22 coal plants. But why? Because they need that reliable power. Because the only thing more dangerous than climate change is not having electricity, which just would kill untold numbers of people, as we see whenever there's a blackout or anything. I mixed up my order here. Yeah, so this is one of these studies. There's a study from 2018 where they compare different grids with different combinations of 100% renewables versus renewables and nuclear working together. And consistently, these systems come out showing that it's much cheaper and easier to go with the one that's a mixture of those if you want to go to really deep decarbonization. So this is this firm low carbon paper. So anyway, all right. I'll speed it up here. So what about cost? Nuclear builds recently in the US have been, in the West in general, Europe and the US have been pretty boondoggly. We built a lot back in the 70s, and then we sort of stopped and we started building them a couple years ago, and they've spiraled. The prices have been too high. We basically forgot how to build large scale nuclear power plants. And so we have a problem with, the cost being pretty high. We do know, however, other places like Korea and China and Russia have basically chosen a specific nuclear design and then built dozens of them, one after the other, and they are able to achieve really excellent cost and schedule performance. And that sort of echoes what the French did back in the 70s. They chose a design, they optimized it, and they built 50 of them. And that was quite efficient and cost effective. And so that's what we need to do again in order to get past sort of the cost overrun issues that we're doing now. And so that's sort of, it's like, okay, so what's the standard design? There's no one in the nuclear industry who's like agreeing on what the standard design we're going to run with is, although that would probably be the best path forward. And then in terms of just costs in general, like when you're dealing with the cost of clean electricity, there's the health impact. So you're already saving huge amounts of money by displacing those health impacts that I talked about earlier. And then of course there's all these different weather related events that scientists are saying, these are starting to become worse and more expensive as the climate is changing. And so as these dollar values rack up, that should be what we're comparing against the cost of building out low carbon energy sources. So point is just that like it's probably a good investment, even if it's a little bit more expensive than natural gas. Fracked methane, I prefer to call it natural. I can't believe they got the word natural into their, what a sham. It bothers me. All right. One thing that's happening in the US right now is that a lot of nuclear plants are at risk of getting shut down early before, they could get relicensed or their license might expire in 10 years. And they're getting shut down early because natural gas is cheaper. Again, high carbon, high air pollution, natural gas just happens to be cheaper. And so the utilities who are looking at the bottom line are like, well, let's do natural gas. And I mean, Indian Point shut down in New York, and like that month, nuclear went down a gigawatt and fossil went up a gigawatt. Like it's very clear again and again. Everyone says, oh, it's going to be replaced with wind and solar 100%. It never is. It never has been. It's always 100% replaced with natural gas, which is like, okay, let's stop doing this. So there's just a couple of weeks ago, I went down to California to join this grassroots rally, which is run by these people here. Like these are the leaders of this effort to save California's last nuclear plant, which is called Diablo Canyon. And they put on this rally, without a permit or anything in San Luis Obispo, which is where the plant is, and said like, it's crazy to close this plant early, but anyway, and so there's a lot of people who are agreeing with that. It is crazy. Like most people, most serious people in energy are like, why would we close 2 gigawatts of clean, low carbon energy in California, where they're experiencing more blackouts and there's, all the impacts of climate change are readily easy to see. And so there's this. Anyway, so if you want something that you can work on right now, like scream how it's important to save this plant. That's like a really, and it's scheduled to 2 plants. One's supposed to shut down in 2024 and the other one's in 2025. However, so it's not outside the US, nuclear plants are being built. There was just a huge headline last month that said China is committing to 150 new nuclear plants in 15 years to help meet its climate goals. That's not a significant, that's 20% of its total current electricity, but still that's huge. I mean, that's more nuclear plants than are in the United States. And there are plants under construction right now in China, Korea, India, Russia, Turkey, UK, and a couple of places. So there's a few dozen plants being under construction right now in the world. I should mention advanced reactors. This is what I work on. There are like non-traditional reactors. We built a bunch of reactors that are mostly water cooled. You can also cool reactors with all sorts of interesting things like liquid metals or molten salt or high pressure gas. And there's reasons you might want to do those kind of things. You can get to higher temperatures, which help you decarbonize industrial process heat. You can desalinate water or make hydrogen at those temperatures. You don't have to rely on backup diesel generators in some of these systems because they can just rely on natural convection of heat through the laws of physics. There's arguments to say they may be simpler, although to be clear, I mean, light water reactors competed with a bunch of advanced reactors back in the 50s and 60s, and light water reactors ended up being much simpler than a lot of the advanced concepts back then. And so it's kind of like, maybe they can be simpler, but we'll believe it when we see it type of thing. There is some of these reactors can actually recycle nuclear waste. So if you don't believe in deep geologic repositories, which you should, but if you don't, you can actually get extra energy out of that. We only take about 5% of the energy out of the fuel in a traditional reactor. And so you could get a lot more out if you wanted. And that will be a big deal if we build thousands of nuclear plants and we start challenging our uranium resources. Then we have to go to these breeder reactors. But until then, like we should just get, I claim we should just get regular reactors kind of up and running. And so, just focus on economics first. Some of this reprocessing stuff ends up adding some extra fuel cycle costs. And that's associated with better sustainability. So like you may hear, oh, we're going to run out of uranium. Well, if you switch to breeder reactors, which has always been the plan, you will run out of uranium in about 4 billion years if you powered 100% of the world's current primary energy. So it's basically, the sun will have boiled all the water off of Earth well before that. So anyway, advanced reactors, good stuff. And I'm happy to talk more about that if people have specific questions. So anyway, I'll wrap it up here. Nuclear is a super interesting and capable energy source. We know pretty much for a fact that we can rapidly decarbonize huge fractions of the world's energy in partnership with the other low carbon energy sources. We have great solutions for nuclear waste. We do need, there's like practical issues in terms of, we need to like deliver better on our projects in the West, but it should be doable. And anti-nuclear messages have been the tradition for many years. Just recently, I mean, some of the recent polls are coming out saying that like more than 50% of people in the United States are supportive of more nuclear because of climate change. And that's like new. It's been like less popular than burning oil for many years. So it's kind of like there's this, when I first got into nuclear, I was like, oh, that's so bad. But then I took a class on it. I was like, oh, wait a minute, this is actually super interesting. So, watch out for that kind of thing out there. And okay, so I'll stop with the slides and open it up. Is there like a chat or anything?
There is a chat in Zoom, and we only have one question so far, and that's from our very own Lila about the intermittency slide. So I don't know if you want to leave the slides up or not.
I mean, I can leave them up. This one.
Yeah. So this is for the whole state of California.
Yeah, pretty much. Yeah. This is the CAISO. I went to the CAISO website, which is pretty much most of California, and just pulled like their demand and supply for a particular day.
Great.
One in the summer and one in the winter.
So please,
Washington,
go ahead.
Would Washington be kind of comparable? Would that be, or we would see even less because we don't have as much sun?
Yeah, for solar, it'd be much worse in the winter. I mean, the seasonal variation would be dramatically worse for Seattle. Like in the summer, it'd be pretty, there's a lot of sun in the summer, but in the winter, there's like none because, the sun goes out at 4:00. And so there's some, but there's very little commercial scale solar in Seattle. We're fortunate because we have such, unique and fantastic hydropower resources. So we don't really, we won't ever be solar powered because of the hydro. But anyway, in other northern parts of the world, like you go to the UK or Scandinavia, you have similar seasonal. The seasonal, we talk about batteries for a day, which, there's something to be said for kind of taking that peak off as the sun sets. But when you start talking about seasonal variations, it gets much harder. You basically have to overbuild. You have to build, if your peak demand is, 30 gigawatts, you have to have 90 gigawatts of capacity. And like some people will say, well, that's fine. We'll just build 90 gigawatts of capacity because it's so cheap. And that's kind of the current like green narrative. And then you have to build, 23.3 gigawatt days of energy storage, and assume there won't be a volcanic eruption that'll cut your solar by some small fraction, whatever. But, and really, to be fair, like nobody proposes 100% solar. It's always 100% solar plus wind plus hydro plus batteries. And so this is a simplification of what the reality would be. But it's just to show, like, it's just trying to sort of talk a little bit about, I'm just trying to show graphically what the intermittency, the seasonal intermittency kind of looks like.
Can I interrupt just for a minute and tell people I totally forgot, of course, to tell people that January 11th, Seattle Friends of Fission is going to have our next speaker, who actually is a co-worker in a sense, I guess, of Nick's from TerraPower, talking about the Natrium reactor, which is going to be one of the new generation reactors being built in Wyoming. So just keep your eyes open for our publicity for January 11th. Thanks.
So I see we have a friend of ours, so I'm going to go ahead and let you ask this question, with your voice. But I'd ask anyone who's not familiar to us, ask it in chat, and maybe I'll be able to unmute you afterwards if you raise your hand. We'll just try to keep this nice and professional while we can. So Chris Bergen, here we go.
Okay, thank you. Quick question. France has lost some support recently, and I think part of it might be because of their visitor centers aren't being utilized. Should we be looking to build visitor centers on the edge of small modular reactors and our large reactors as well to work on public support?
I mean, yeah, I think that's a great idea. I mean, I think the nuclear industry in general, like through the 80s and 90s, decided to just like hide. I think the overriding thought was like, if they don't think about us, they won't protest us. Because, it just became so unpopular. And so they just like have been producing all this low carbon energy. And like in France, you survey, like, is nuclear low carbon? And something like 60% of people are like, no, it's high carbon. Nuclear's high carbon. Like, how could it even be high carbon? Like, I don't get it. But so it's visitor centers, Boy Scout, Girl Scout visits, education. Like, people should be going into classrooms and giving some talks about like, hey, nuclear power is low carbon. Like, at least say that it's low carbon, because so few people understand that. And there's lies, like straight up lies of people, in big green NGOs, who just say like, oh, it's high carbon, and they just make it up. I mean, there's like actual examples of them saying like, well, nuclear says it's low carbon, but we're just going to increase it by like 200 grams per kilowatt hour because we don't like it. Like, and then they put it on the graph. It's crazy. So yes, there should be visitor centers everywhere. And, after 9/11, we sort of like locked down. It's really hard to get a tour of a nuclear plant these days. And that's unfortunate. It's just the nuclear industry punching itself in the face kind of thing.
Great. So we've got a few questions now in Zoom. First from Katie, comment, Yucca Mountain is a very bad geological area. And we, of course, have heard this from Jim Conca. If you check out our latest here on YouTube, Jim Conca, What About the Waste, aka the billion-year secret nuclear waste repository. There's my clickbait title. That's talking about the waste isolation pilot project. Nick, do you have any comments on Yucca Mountain before I get to Katie's question?
Yeah, I mean, as Jim Conca has explained, like, it's not, there are things about it that are not ideal, and he prefers WIP, for instance, and crystalline bedrock is nice. And so, yeah, like, it has, there's certainly things to be, unhappy about it as a site, besides just the political siting issues. But on the other hand, I mean, it also has been subject to like dramatic amounts of geologic study, and some of the best geologists on the planet have studied it and basically said that, like, yes, we believe it is responsible and appropriate to put this material in this site. Is it perfect? Absolutely not. But is it appropriate given the relative risks? According to the experts, yes.
And Katie's question, do you know anything about the deployment of small modular reactors planned by GE and Rolls-Royce?
Not too much. I mean, so yeah, GE just got selected by a Canadian utility, OPG, to build a BWXT 300 in Canada. So that's like a new big project that GE is going to be working on. Rolls-Royce has been focusing more in Europe. But yeah, I mean, it's like everyone's looking for customers and places where, someone who needs power is willing to sort of take a first of a kind type risk to build. A lot of these are like, they call them small modular reactors, but I mean, 300 megawatts is medium in my opinion. So there's still, there's investment risk and whatnot. So a lot of first movers are like, I want the second one. And getting that first one can be a challenge. So yeah, some of those things are still in flux.
Question from Eugene. Where are the best places to site a nuclear plant in Washington? How much more and how much would we need to reliably export clean nuclear power to California? I guess we could break that up as like, how do we backfill what's shutting down, or maybe how do we eliminate fossil fuel use in California?
Yeah, there are a bunch of coal plants in Nevada, like right on the border of California, where they're like, okay, we'll just do coal and then we'll just import it into California. So yeah, I mean, it's not a crazy idea. So Diablo Canyon, which is a 2 gigawatts, 2 units, each 1 billion watts, produces just about 10% of California's total electricity. The entire state of California, it's roughly 10% of their electricity. So you need about 10 Diablo Canyons to power 100% of California's electricity. And that said, we're trying to electrify cars and buildings and get rid of industrial process heat. And so you could sort of imagine we need to like double-ish the amount of electricity used. So we would need, so really like the right answer is like 20 Diablo Canyons would basically provide all of California's power. Getting it from Washington State to there, I mean, yeah, it could be done. It's not, get some transmission lines going. It's a bit of a distance. There are losses on transmission lines. The best sites, I mean, our only nuclear plant is out on the Columbia River, basically on the Hanford site. So that's where Columbia Generating Station is. It's a big, there's a lot of cooling water in the Columbia River. So that's a good place. We also, I mean, out by Olympia, there are 2 not completed big nuclear power plants that were part of what we jokingly call whoops at SATSOP. So that's a acceptable site. There's quite a few sites that are acceptable in the state. I mean, we just have so much water and anyway. So
looking at my map of U.S. power resources from Phil over at Americans for Nuclear Energy, I'm reminded that SATSUP, in fact, has been replaced by a 637 megawatt gas plant.
Yeah, so it uses the same roads and transmission lines.
Yeah.
Another example of a nuclear plant that didn't get built being replaced with gas.
So what changes, if any, would you make to the current regulatory regime in the U.S.? As someone who listens in on the NRC public meetings, it appears to be Kafka-esque.
Yeah, it's a good question. I mean, it's easy to rip on the NRC. They're just trying to do their job, and there's a lot of people they're answering to, which has been challenging through the years. And they've set up, they've responded to some issues in the past by going to different types of licensing. And they are working on this thing called the Licensing Modernization Project, which has a ton of work going into it that tries to be sort of more technology neutral and risk informed. And they're getting a ton of feedback from the industrial players. And so they're really kind of open to discussions along those lines, trying to sort of make the regulations not so specific to water cooled reactors. There's a lot that has to be kind of shaken down with them. I mean, I guess it would be nice if they could sort of consider, they don't really do this, but I sort of wish they would consider like the risks in the sense they're sort of comparing like, should we build the nuclear plant versus do nothing? But I wish they would sort of pull this slide up and say, should we do the nuclear plant or should we build this high carbon, high combustion natural gas plant, and sort of compare the risks in that sense, and then sort of adjust the regulations to be ratcheted a little bit more appropriately based on that kind of alternative. That's kind of hard because it's already ratcheted pretty far. But yeah, that could be better. And then in terms of, there are some things that like the industry could do to try to help out in that regard as well. Like there's these quality assurance standards that like, if you buy a valve that's safety related, it has to have this like pedigree with it. That's just this mountain of paperwork and all this testing. And it's not actually clear that paperwork and testing makes the valve any more reliable than like a commercial one that you get off the shelf. So there could be some like research done on like, let's build 100 under those quality standards and 100 under just commercial grade standards and prove whether or not that's appropriate from sort of a risk perspective. So anyway, I'll stop there.
Oh, and I want to give a quick bit of advice to the nuclear advocates in the room. We need to participate in the NRC public comment process. Mm-hmm. There are, of course, people whose hobby is to speak out against nuclear We had 4 people or 3 or 4 people speaking against nuclear in the Washington State Legislature against Bill 5244 that we are now organizing in favor of. And I was the pro voice as soon as I heard of that bill. So we're happy to help everyone in the audience today organize around public comment and show you how you can do that, how you can make your voice heard. A question from Sigdom. I heard from Jim Conca they don't know how to assess the safety of a molten salt reactor, and it would be great if they figured it out.
Yeah, I mean they rely on the science. You know, they look at the national labs. They get expert consultants to come in and say, like, what's going to happen if fluid fuel that contains fission products at 700 Celsius leaks out or like goes out of stack? Like, what happens? Like, where do the fission products go? And no one, like, that's just, I mean, we know some of that, but we only ran one of these reactors back in the 60s, and there's only been a handful of experiments along those lines. And so there are tons of experiments to sort of answer those questions going on now, because molten salt reactors are so interesting and popular at the moment. And so, yeah, I mean, you have to like build the scientific basis for the safety before you make a judgment on it. And so, like, they're sort of in a tough spot, because you can't just say like, yep, it's safe because, you know, Kirk Sorensen said it's safe. Like, you have to have a scientific basis for safety. So, and anyway, that's being built up rapidly. And in fact, China has just built like a thorium fueled molten salt reactor, just like what we had in the 60s. And it's like about to go critical any moment. I'm like watching the headlines. It's like they really, so anyway, that's super exciting.
Oh, good. So you pay attention to that perhaps better than I do. And I saw that the one that's about to go critical, is that the test scale, like the 5 megawatt scale, or is it the 100 megawatt?
Yeah, it's the test scale one. It's like, I thought it was it 5? I thought it was like 2 or 5 or something like that. But yeah, it's a handful of megawatts. It's similar to MSRE that we built in Tennessee.
Yeah,
but they are actually putting thorium in it, which is fun. We never put real thorium in ours because it's a neutron poison before it breeds. So, but I think they're just throwing some in, you know, because that's the whole point, is to sort of do the slow neutron breeder reactor.
A question from Lila. Can you talk about microreactors?
Sure. Yeah. So microreactors are interesting. I would say they're basically a response to the issue that like these big super mega projects have gone way over budget, and like there's no utility that can like buy one of those mega projects right now without worrying about going bankrupt, even if it's like the world's biggest utility. And so like the appetite for risk for huge mega projects is just not that high in places other than China, Russia, India. And so microreactors are like an interesting way to do nuclear technology and find fringe applications, remote mining towns, remote villages in Alaska, military bases, space, the moon or Mars. Those are all like great places where microreactors might be super interesting. And because they have capabilities, like they run for decades without refueling, that's a lot easier than shipping in like a truck of gas, a truck of diesel, many trucks of diesel like they do in some of these Alaskan villages and whatnot. And so it can be sort of an interesting application. I'll say, and then there's the concept of like, maybe you can mass produce them. Like if you just like make an assembly line of these things, maybe we could get costs down as well. And then you could like scale out, and you can start imagining like nuclear farms, with hundreds of microreactors in a field. That could be, I'm like a little bit skeptical of that concept. I think it's always going to be, your economies of scale are still going to exist. And I think for powering mega cities, you're going to want big power plants. But anyway, that's kind of the idea.
So one of my regulars, it's related in chat, says, I wouldn't mind 5 megawatt laying around to sell to everyone nearby my home.
Yeah, but are you gonna like? There's security people, there's trained operators, 3 shifts of security, 3 shifts of operators. So like, yeah, but it's pushing some interesting conversations. Like they're saying, well, can we make autonomous reactors that don't have any operators at all? And everyone's like, oh, maybe, but like that's like the NRC is really not ready for that. I mean, the grid operators can't even like request more power without like a nuclear operator saying like yes. Like, so anyway, it's going to be hard to get to the world where we have no security and no operators. And in that case, like if you're going to have 5 operators, you might as well make a 2 gigawatt plant.
Question from Christopher. Do you think it would be possible to replace the 4 dams on the lower Snake River with an SMR reactors? He asks in the hope of benefit to Friends of the Clearwater.
Yeah, I mean, I think that's an interesting question. And that certainly, I think that is totally feasible. You still would be pulling, the thermal effect of the nuclear plants would be a lot less than the total impact of the dams for sure on the ecology of the river. So yeah, and the sizing could be pretty related. So that's actually not a bad idea. I mean, if we really do want to get rid of those dams, it'd be a shame to get rid of the dams because we're so low carbon here in Seattle. Like, we certainly don't want to take those dams out and replace them with gas. So replace them with nuclear would be quite interesting. So I think that's a great idea.
And Christopher follows up, can you compare safety cases of fast and slow molten salt breeder? So I think he means fast and thermal.
Yeah. I actually say fast and slow now because thermal is super confusing. Like the neutrons are either fast or they're slow. Thermal. Anyway. So I mean, it's kind of like, it's hard to say. Like fast neutron molten salt reactors have never been built, and only 1 or 2, actually 3 slow neutron molten salt reactors have been built. And so it's hard to like say, you don't really know the full safety case of a system until you've built like a fleet of them and you've kind of shaken it down and seen what kind of different things happen and how the various systems behave. But like inherently, I don't know. That's a tough question. The fast neutron systems have a lot higher concentration of fissile material, but it's a lot harder to fission it with a fast neutron. Anyway, it's sort of a wash. I can't really say anything too specific on that.
Our friend James asks, is there any effort in the U.S. to use microreactors to power commercial seagoing ships?
Let's see, not necessarily in the US. There are a few companies that are working sort of globally on replacing merchant shipping power plants with nuclear plants, like what Savannah was back in the 50s. And that's a super interesting and fantastic application of small reactors as well, because, again, we have hundreds of floating nuclear power plants in the military, and the Russians have a few nuclear powered icebreakers that are just awesome. Like you can go to the North Pole. You can actually, you can buy a tour on a nuclear powered icebreaker to the North Pole like next year. It's $40,000, but you can buy it. So anyway, yeah, that's a really great idea. The old day challenge was that, burning fossil fuel was cheaper and easier to, you don't need as many people to maintain and operate the thing. And so it all comes down to economics. So if you want to put, this is where like things like carbon taxes come in. If you have a carbon tax, then all of a sudden the economics of fossil sources is much worse, and nuclear all of a sudden looks very interesting. And in terms of powering a ship quickly across the ocean, nuclear is as good as it gets.
Well, we've got quite a bit of text from Katie on the geology of Yucca Mountain. A few things interesting here that maybe we could bring in a geologist like Jim Conca to talk about.
Yeah, you definitely want Jim Conca to talk on this topic for sure.
Yeah.
I mean, there's also, I mean, these are reasonable concerns, but there's also, there's counterpoints to a lot of this, and so it's not an obvious no. It's been studied in detail, and there are serious questions. And Jim Conca can certainly talk to this a lot more. And he'll agree. Like he does not think Yucca Mountain is an ideal site. So.
Yeah, some of these are a little interesting to me, like the volcanic hazard estimates, which we do have a fair handle on. We know where these subduction zones are and where the caldeiras are building up, and things like carbon-14 releases is, of course, an issue that Greenpeace has tried to use in the media.
Yeah,
on
exactly.
Fukushima.
And which I debunked instantly by saying that the amount of carbon-14 in the Fukushima tanks, that the total amount is made by the sun in our atmosphere every 2 seconds or something like that. So it's and it may be different with Yucca Mountain, but carbon-14 is generally not because it's created, naturally. The amount compared to the natural background is usually very much in the noise. But Jim Conca is going to be the expert on this. He has studied Yucca Mountain in elaborate detail. I have not.
I'm seeing we're running out. Oh, there we go. Tom asks, are you involved in the molten chloride reactor experiment? So if you don't mind, I'd like for us to know a little bit about your position at TerraPower and what you can tell us about the molten chloride reactor and the project we're going to hear about in January, the Wyoming plant.
Yeah. So, okay, sure. So TerraPower, started by Bill Gates many years ago, has been working on a couple different reactor projects. One is now this liquid metal cooled reactor that's going to be built in Wyoming. And the other is a small test reactor experiment called the Molten Chloride Reactor Experiment, which is part of a molten salt fluid fuel fast neutron power plant program. And so we're starting small with that one, but we're not starting small with the sodium cooled one because we've built dozens of sodium cooled reactors in the past. So I've been just tangentially involved through the years with the molten chloride reactor experiment. I gave the presentation to the board about molten salt reactors many years ago that convinced them to invest in molten salt reactor program in the first place. So that's my major contribution. I got up there, was like, look, molten salt reactors are awesome. They're like, cool, do it. And so, then we hired dozens of people who did all the real work and have brought it together. So I've been sort of tangentially involved, but not super heavily. I wouldn't say I'm crazy involved in it. It will be the first fast neutron molten salt reactor in history if it's on schedule, for sure. That is true, at least that I'm aware of. There's always something in the weapons labs. And that's going to be in Idaho National Lab in partnership with Southern Company. My position, I did reactor design for many years, mostly on the sodium cooled side, and I've been at TerraPower for 12 years, which is insane. And I've recently stepped just a little bit back from the my normal core design stuff, and I'm working on kind of higher level stuff that's really focused on trying to get cost performance of nuclear design projects to be more efficient. Having turn the crank for so many years, I've decided that sort of basic things why is the dimension of the cladding tube what it is, what are all the decisions that went into that, and how do we trace that back, and if we want to change it, what do we have to reconsider? Sort of organizing that information using modern computers and databases is what I'm currently focusing on. So it's like a software project as opposed to even though I spent all this time studying reactor physics. So that's what I'm doing now.
That's just amazing. My personal story, I know a couple of the Friends of Fission have great personal stories, and we might develop a programming around this. But my personal story is that my dad worked on SATSIP, and in fact, he had a luggable 8086 computer where he programmed the accounting and reporting system for the many different subcontractors that what's now Energy Northwest used to manage that project. Is absolutely gigantic compared to anything else that we had taken on in the 70s and 80s. And so it required custom software to track those invoices.
Yeah, totally. And it hasn't been fully leveraged yet. It's still, when you look at the cost, it's just the cost of engineering is going up, not the cost of steel and concrete, interestingly. So that's cool.
We've got a couple questions. Eugene asks, what is the smallest or the lightest weight reactor that you know of? And he's wondering because SpaceX Starship could lift 100 metric tons to low Earth orbit.
The smallest is like a 3-kilogram beryllium reflected sphere of highly enriched, pure plutonium 239. But no, realistically, I mean, you may have seen something called Kilo Power or the Krusty experiment, which is a very small reactor that NASA built, I don't know, 3 years ago or so, sort of to scope out that type of thing. It had it's like this big, it's like a tabletop reactor. Not very high power, a few 100 kilowatts, if I recall. And then, I mean, like I said, the Soviets launched several dozen nuclear reactors that powered satellites whose job it was to look for US submarines under the ocean. So they were pretty high powered. I'm not sure exactly. I can't remember their rating, but those fit in a single rocket back then. But when you're talking about reactors for moon bases or Mars bases, you're not usually going much over, a few megawatts. Like it's not until you're going to build like a city out there. But if you're running 5 megawatts in the vacuum of space, you have to radiate that heat somehow. You don't have an atmosphere or a river to dump the heat into. And so you have to build these like excessively large radiators to just radiate the heat straight to, some low atmospheric pressure or to a vacuum. And so they won't be super big at first. So the current rockets are totally capable of lifting lots of nuclear reactors up into space. And then, of course, there's this concept of nuclear propulsion. So you can actually have nuclear propelled rockets, which are super interesting because they go much faster and carry much less fuel than a chemical rocket. And so you can get to Mars and back dramatically faster. Or if you want to go somewhere else, obviously the Enterprise is nuclear powered.
Let's see. Christopher asks, are fast MSRs more prone than slow MSRs to prompt critical accidents? So of course the characteristic, and I gotta say the characteristic of prompt criticality is not something that we find in I think any nuclear reactor. Is that possible in any nuclear reactor at all?
Yeah. Oh, yeah. It's possible. I mean, that's what happened at Chernobyl, for instance. Chernobyl was a prompt supercritical accident. And yeah, I mean, there's various ways you can get into those situations, but usually you rely on sort of these natural feedback. So like if you boil your water, then, well, the water was doing a job. It was slowing down the neutrons. And so if the water's gone, the chain reaction stops. And so we do design most reactors so that it's really unlikely or difficult to postulate something that would make a prompt critical accident. Let's see. So are fast or slow? I mean, it's hard. It's a little bit hard to say. Kind of depends on like what the moderator's doing. Like if the moderator melts or ejects or something, you can have some dynamics, but fast neutrons generally have fewer delayed neutrons. And so they're like closer to prompt criticality. But anyway, again, because no one's ever run to fast or slow MSRs, like we do not understand or have information about the detailed characteristics of their various core damage frequencies. Like that information does not exist at the moment.
Tom comments or asks, Triga reactors, do they?
Yeah, exactly. Yeah. Yes, they do. And then they immediately cool off before causing any damage because as they're heating up, the moderator, which is the hydrogen atom, starts vibrating so fast that it speeds the neutrons back up. And so they stop causing fissions. And so the thing stops. So you can go on YouTube and you'll see these, undergraduates shooting the control rod out of a university reactor. And it makes this awesome shrink off blue glow, and then it just everything goes, and you can see that if you look at the power, it comes up and comes down really fast, and that is a prompt criticality for sure.
Kevin asks, for folks wanting to spend their careers in nuclear, what skills, technical or non-technical, do you recommend that they develop to maximize their impact?
Let's see. The first part was people who
want
people who are trying to
Yeah,
Yeah.
get into nuclear and really, you know, make a big impact in the field.
Well, yeah, that's a good question. I mean, make a big impact. Like if you can convince the world to all standardize on one reactor and then have everybody build that one, that would probably be the biggest impact. My favorite concept of doing that is to like have a shipyard construction where you just like build the same reactor in a shipyard and put it on a floating platform and deliver it out from the same site. So if you could like start that company that existed in the 70s, it was called Offshore Power Systems. Anyway, that'd be a huge impact, but that's not skills necessarily. For just day to day, like if you want to get into nuclear and work on some of the design projects, I mean, skills that like in nuclear engineering schools or just mechanical, any engineering school, people like are really good at doing various analyses, but no one is that good or that well trained at like information management, which again is kind of my thing, but it's like everywhere. We're all information workers these days. And so if you can know like a little bit of Python to be able to like pull data from a thing and do it in a way that isn't just real manual and convoluted, that'd be super useful. So like coming in with some like basic programming skills in Python or something would be very useful. That's like a huge, I wish they taught that in like middle school instead of long division. Because I'll tell you, like the amount of time that I need long division out of people at work is like never. I mean, even like calculus, we use in the codes, but like just being able to do basic data management and regular expressions and like use a computer and the command line, that would be so useful and so great for everybody. Anyway, I don't know how impactful it'll be, but that's like what we struggle with sort of in the day to day. I will also kind of say like we don't really need more reactor concepts. As a joke, I like made on my webpage, I made whatisnuclear.com/random, which will give you like a random reactor concept just generated from a script. New reactor types don't like we don't necessarily the biggest problems in nuclear are not necessarily related to the design of the reactor. They're more on project delivery and project management and that kind of thing. And so don't focus too much on new reactors if you're trying to get into it. I mean, on weird different types of reactors, but rather just try to get the economics of what we can do right now done as soon as possible. And then once we have like a thriving fleet of, you know, these economical low carbon reactors decarbonizing the world, then we can start looking at the more advanced capabilities as appropriate, if that makes sense.
Well, I think we're running low on. Oh, there's one more. So I'm going to make this our final online question. We're going to cut broadcast and then give everyone permission to go camera up and turn on their microphones. And after we say goodbye to Twitch, YouTube, Facebook, DLive, you know, all these great networks. I hope you enjoy this content. The principal channel for this content will be the Seattle Friends of Fission on YouTube, and we're gonna make sure that VOD is trimmed down and really easy to watch. So the final question: what is your take on fusion companies, compact fusion or ZAP? Or designs that are starting to get traction?
Yeah, there's been some like real exciting news and investment in fusion companies. A lot of my friends like work at Commonwealth Fusion in Boston, and I think they're doing pretty good work. I actually got into nuclear because of fusion. I was like, no, fission, that's bad, but fusion is awesome. And so like I joined the nuclear engineering department to do fusion at first and switched over to fission once I realized it was like pretty good as well. I certainly believe we will accomplish fusion as a power source at some point, and I'm pretty excited about it. I will also say that like there's going to be huge headlines as soon as we like break even with fusion, but like that's just the physical viability of the like concept of fusion as a power plant. And then you have to still come in and like convert the heat to electricity with some kind of system. And then you have to like do that in a way that doesn't use all the rare earth magnets of the world, which, you know, you could use it like what people are doing these days is like high temperature superconductors, things that are a little bit less rare, at least maybe more exotic. But anyway, you still have like natural gas out there that you have to beat. And so if you make a power source that's like 1,000 times more expensive than natural gas, even though it's fusion, like you've done nothing, like it's cool, but like you're never going to use it for anything. And so it's not a sure thing that just if we make a fusion power plant that it's going to be even remotely economical, especially at first. And so anyway, I'm excited about it, and it's absolutely important to be investing in it, and people who want to invest in it, like please do. Like I think that's a good use of money. I don't recommend doing it as like your investment, like or for your retirement. Like don't rely on it if you need the money. It's probably not like the world's safest investment, but I mean I think that's pretty easy to understand. I mean anyway, so that's sort of that summarizes my thoughts on it.
Great. Thank you so much. And just to wrap us up, we again want to remind you that the Seattle Friends of Fission is going to be hosting Nick's colleague Mark to tell us all the details that he can about the natrium reactor project in Kemmerer, Wyoming. I in fact found that someone else here on Twitch Politics has. I need to.
Sorry.
No, it's fine. I know how to fix this.
I just closed the thing. I can reshare.
No, I got it. I've got my program up so that I can select cameras now. So
cool.
The Kemmerer, Wyoming project is actually his great grandfather was the namesake of that plant, and so we've got these little connections here and there, and that coal plant is going to be replaced by a clean fission reactor. So very exciting. Again, that's January 11th. Check us out, Seattle Friends of Fission, on Meetup, on Facebook, and on YouTube. Depending on if you would like to participate in the Zoom meeting or if you just want to check it out during or afterwards. So